All right, welcome everyone. Hello and welcome to session 6013, Satellite Earth Observation, a unique view of our planet and a critical need for Canada. This is part 4 of our session. You can see the speakers lined up for today. Bonjour à tous et bienvenue à la session 6013, l'observation de la Terre par satellite, une vue unique de notre planète et un besoin critique pour le Canada, partie 4. Before we get started today, I'd like to begin by acknowledging the Indigenous peoples of all the lands that we're on today. When we meet today on a virtual platform, I'd like to take a moment to acknowledge the importance of the lands which we each call home. We do this to reaffirm our commitment and responsibility in improving relationships between nations and to improving our own understanding of local Indigenous peoples and cultures. Today, I'm joining from Ottawa on the unceded, unsurrendered territory of the Anishinaabe Algonquin Nation, whose presence here reaches back to time immemorial. I encourage everyone listening to learn more about the lands where they are based and the past and present of the Indigenous people who live there. So today we've got a great panel of speakers lined up, and we're going to start. We have a number of surface observations, mostly cryosphere focused today, a bit of a change from our atmospheric focus yesterday, and we will kick things off with Alec who's going to talk to us about using RADARSAT observations to investigate Arctic lake ice phenology. So please take it away, Alex.
All right, I'll just share my screen now. All right, so hello everyone. My name is Alec, and I am currently a postdoc at Department of Geography, Geomatics and Environment at UTM, working under supervision of Professor Laura Brown, and I'm also a visiting scientist at the Climate Research Division of ECCC. And what I'll be presenting today is some early work we're doing with using RADARSAT observations to investigate Arctic lake ice phenology. And that's investigating the freeze up and breakup timing of Arctic lake ice, which you can actually see pictured in the background here. For context, this is from North Lake on Cornwallis Island, and it's about 2 meters thick. I took this photo during a recent field campaign of ours back in May this year. So without further ado, I'll continue on. First, just some background on lake ice and kind of why it's important and what we're looking at. So for context, Canada has access to approximately 20% of the world's fresh water, much of which is contained in lakes. And of course, as we know, with climate change, global warming, we are experiencing a tendency toward earlier ice breakup. But we're interested in investigating exactly how much earlier this is happening and how the freeze up is being impacted as well, particularly in Arctic lakes. However, Arctic lakes are often in remote locations. They're logistically challenging to observe in situ. For example, here's a photo from our recent field campaign. And this is Laura Lake on Cornwallis Island in Nunavut. And you can see here that we actually had to fly in on an airplane because it's difficult to access otherwise. Some of the local residents will travel by snowmobile instead, but that's a 6-hour snowmobile ride from the local community of Resolute. So it's quite a while away. To investigate lake ice, then, we can use different means in addition to in situ observations. For example, lake ice models, which I'll be discussing more on my talk on Thursday. But for this particular session, I'll be looking at estimating freeze up and breakup dates from remote sensing observations. And so the remote sensing observations I'll be using in this case are the RADARSAT Constellation mission, RCM, a mission from the Canadian Space Agency. Briefly, this is a constellation of 3 identical satellites in sun-synchronous orbit. And the nice thing about these instruments is that they have very frequent sampling at high latitudes, particularly in the Canadian Arctic, which is at least sampled at least daily by these instruments. So we can see day-to-day changes in the lake ice cover. Each of these satellites is equipped with a C-band synthetic aperture radar. So we're getting radar imagery of the ground. And C-band is particularly good for measuring ice, commonly used for sea ice, but it also has utility for lake ice as well. And the horizontal resolution that we're using for this work is the 100-meter and the 50-meter products. However, even with these resolutions, which aren't the highest resolutions available from RADARSAT, we do find that we get quite good imagery. I'll be showing that in a few slides. And so again, some previous work has investigated this for lake ice, so we're kind of continuing from there. Now, we're doing a case study for a particular lake. So this is Eleanor Lake on the left, pictured with the indicated with a red star. So the nearest sort of community there is Cowswittook or Resolute Bay, and it's on Cornwallis Island. Again, this is a rather remote location, but it is actually used for fishing by members of the local community. So this is a lake that, although it's remote, there is still some human activity on it. And there's just a zoomed in, just visual image for context of how this lake looks. Now, we're supplementing these RADARSAT measurements that I'll be discussing in a moment with in situ camera observations, which are taken by trail cameras. So for context, the location of our trail camera site is indicated on the map on the upper right, and a sample image is on the left from March 20th of last year. And so these trail cameras observe lake ice freeze up and break up. You can see just in the photograph that currently in that photo, it's covered with some lake ice, and there's a little bit of snow cover, but there's patches of open ice as well, or bare ice. And these cameras take one image per day from 12 to 1 p.m., same time every day. They're just pre-programmed. The caveats of this is that the view may be obstructed by precipitation. Occasionally, when it's quite stormy, the image may be blurry. And the camera may also actually get turned around sometimes by animal activity or by weather. Thankfully, that did not occur for this particular site, but our other sites did experience such issues. Furthermore, the view of the camera, as you can see, does not cover the entire lake. This is actually done deliberately in consultation with members from the local community who understandably may not necessarily want to be in photographs of the lake. And so we consult and see what a good direction to point it in, where we can see some of the lake ice surface, but we're not seeing where people are actually going to be, fishing or walking on the lake or traveling over it. And so the images that we examine are from August 2022 to December 2023. So we have just over a year of images. And just an acknowledgement to Debbie Ikaluk, who downloaded these images from the camera for our group when we weren't able to make it up to the camera and demo the images from it. So now going back to the RCM, here are some example observed backscatter images. So just single images for the low resolution and the medium resolution modes. Now this is just from the HH like polarized band, but the cross polarized band looks relatively similar. And so you can see that even in the low resolution mode, we can actually see quite a bit. It's quite good resolution, all things considered. We can still see quite a few details. This is in August 7th and 8th. So this is right when the ice is more or less broken up completely over the lake. But this is just an example of how this imagery looks. And acknowledgement to Mike Brady from ECCC for doing the pre-processing for these images that helped with the analysis. Now, I mentioned that we have daily images or even sub-daily images. So here's just a few day-to-day changes in ice cover from the RADARSAT RCM imagery and the imagery from the camera. So these are, again, images from the same camera. You can see the same angle. Looks a bit different because here it's mostly melted. So this is from August 3rd through to August 6th, when the ice is just kind of breaking up and going toward full ice off at the end of the cold season. And so what we see is that there are some scenes in the camera imagery where the lake surface may appear more or less ice-free, for example, in the first and the last images, but we can still see from the satellite imagery that there are ice-covered regions in the lake. One thing that's also nice is that we can see how parts of the ice get rafted across the lake. So this can depend on the activity of wind primarily, but it's nice that we can, because we have these daily and even sub-daily images. I'm just showing single images from each day, but there are actually multiple images per day for most of these cases. And even so, we're able to see quite a bit of the evolution of the lake. So it's an asset not just for looking at the entire lake, but also for looking at how the ice behaves on the lake itself. And finally, just for context, again, discussing resolution, The third image for August 5th is a medium resolution image, whereas the others are low resolution images. So even in the low resolution images, we can discern quite a bit of the ice. So now this is just a time series of the averaged observed backscatter over the entire lake, just to give an idea of the seasonal evolution of this backscatter. And so this is shown, band 1 here denotes the lake polarized band, HH, and band 2 denotes the cross polarized band, HV. And so the blue lines indicate periods of freeze or freeze up, and the gray line indicates snow on, whereas the red lines indicate the start of the melt and the full ice off. So the key point here is that we see that from the start of the season around October, we can see that once there's ice on and snow on, those happen quite coincidentally based on the camera imagery. We see that there is a steady ramp up in backscatter in both bands. And throughout the cold season, there is quite a bit of variability. A lot of this is likely due to the fact that the snow cover is not uniform on the lake. It actually does end up being redistributed over the lake, and there are times when the lake is almost bare. Nevertheless, once we get to the warmer season, we see this drop off in backscatter, followed by this sort of abrupt spike between June 24th to August 8th, during the period between when melt starts and melt ends. And then, but on August 8th, once the ice is fully off, we get this abrupt drop in the backscatter again. So these are signatures with which we can discern then when the ice off happens. Ice on is more difficult to detect because it's kind of gradual and there's intermittent melt and refreezing, especially in the 2023 kind of October-November period. But nevertheless, this is ongoing work, but we're able to discern some parts of this already. So now, for additional context, here's a 3-year time series to see multiple seasons of this. And below that, I've plotted the station temperature from Resolute Base Station, from the weather station, for comparison. It's not a coincident location, but it's relatively close. The cameras do have temperature information, but it tends to be skewed because of the fact that it's being measured on the camera itself, where the chassis of the camera can be relatively warm by the sun, for example, so it's not a very robust measurement. In any case, what we see is that there is an increased backscatter. This sort of period of brief increased backscatter before falling off again happens during the melt period of each year, as we expect. And also, furthermore, the melt onset is strongly associated with the onset of above zero station temperatures. This is kind of to be expected, but it's nice to see directly how the backscatter signal is associated with these higher temperatures. Conversely, the onset of freeze, which happens later in the season when we see this increase in backscatter gradually happening again, that lags the onset of the freezing of the below zero temperatures. And again, this is partly just due to the fact that freezing is a gradual process. The ice doesn't form kind of immediately. And also we do get periods of periodic freeze and thaw before the ice fully freezes up. Finally, just a note on quality control, you may see some spurious high backscatter values in these plots where occasionally there's just a very high spike. Those are spurious values that are just, the entire seam seems to be very high backscatter. So we're working on some quality control to filter those. But this is sort of ongoing work. But as a first step, we're already able to discern some features. So now just for some conclusions and next steps. So what we found is that lake ice freeze up and breakup can be detected from RCM imagery. We find that there's a strong increase in backscatter during the melt period, which was kind of unexpected, but this is also coincident with above freezing station temperatures. So this can be used as a signature to detect when melt is happening and when melt is complete over the lakes. However, the freeze onset lags the onset of freezing temperatures. So information from the backscatter is needed in addition to temperature information to identify that. Next steps for some additional things we'll be doing with this project is automated identification of freeze up and breakup days from RCM imagery. We'll be using some previous work for that, but that's sort of still in progress. And then furthermore, we'll be examining a longer time series and extending analysis to additional lakes. once that's more established. That's all for my presentation.
Great. Thanks very much, Alex. Really interesting. And it's great to see RCM being used in this now time series of very dense observations that we have from RCM compared to days when I was in academia doing RADARSAT 2, and it was very, you had to work really hard to get a couple images. So awesome to see this great coverage over the Canadian Arctic being used. I don't see any questions in the chat yet, so maybe a quick one for me. I was curious a little bit more about the spurious backscatter, high backscatter measurements on certain days. I'm assuming this is a backscatter averaged over the entire surface of the lake.
Yes.
So wondering if, looking at those days, are they maybe, is it images acquired at a very different incidence angle? Could it be wind? Could it be maybe a georeferencing issue? Maybe some land pixels are contaminating the average? Curious if you have any thoughts on that.
So I did compare with incidence angles and times, and these do show up. They don't seem to be affected by incidence angle, in that when we examine, specific incidence angles together, we still see these spurious values pop up sometimes. What it looks like in the actual scene is that the entire scene just appears to have a higher backscatter. So I suspect this might be just something with possibly an issue with the calibration, I suppose. But that's something that we're still looking into. But in any case, I'm not sure if it would be necessarily wind impacted, because it's not just the lake ice that's being impacted, and it's not the georeferencing either, because I've looked into that. It's just the entire scene is just has a higher brightness.
Okay, well, good luck sorting that out.
Thank you.
And to keep on time, we'll get right into our note. Thanks very much, Alexander, and we'll move on to our next presentation. Greg Smith from Environment and Climate Change Canada will present on the assimilation of synthetic SWOT observations for the Canadian East Coast using the Regional Ice Ocean Prediction System. Take it away, Greg.
Thank you very much, Alex. Just share my screen here. Okay, you should be able to see that now.
Yep, it's up. Thanks.
Great. So yes, what I'd like to talk to you about today is some work we were doing to prepare for a new satellite mission, the SWOT mission, and doing some work on assimilating synthetic observations into our regional ice ocean prediction systems. This was work done as part of a CSA-funded project with collaborators at Dalhousie and BIO and others at Environment Canada with myself. Okay, so a few words about the SWOT satellite mission. So it's a surface water ocean topography mission. So there are a number of projects in Canada looking at preparing for this as part of a CSA-led effort. But basically, the current status is that we use altimetry observations, nadir observations, to get the surface water level of the oceans to help us to constrain the mesoscale features in the ocean, highlighted in the bottom right panel there. And what's new about SWOT is it gives us a wide swath. So instead of having this kind of pencil line measurement over the ocean, we now have a wide swath image, so a 2D image along the swath. And so this mission was successfully launched in December 22, and it's been undergoing its calibration validation phase and getting the processing ready. And so during that time, then we were working on doing these synthetic observation studies. So why SWOT's interesting is because by having this 2D view, it also includes higher resolution altimetry measurements. So as the panel on the bottom right tries to show, it takes us from altimetry that can only measure really the mesoscale features, so the sort of larger eddies in the ocean, down to even the sort of sub-mesoscale filaments. And this can be quite important for applications such as surface drift and estuary and river applications as well. So interestingly, there's also a one-day overpass CalVal phase of this that I know various groups in Canada have been working on, but we're really going to be focusing on here today on the 21-day science orbit. And real observations from what have actually become available recently, and so I'll show some early results from the assimilation of real observations as well. So a few details about the satellite itself. So as I mentioned, it goes from having a single sort of one-dimensional measurement over the ocean. We see in the center here, this nadir measurement, to now having a 2D 120 kilometer wide swath, which opens up the door to a variety of different types of applications. So in addition to having this wide swath, then it also has a greater resolution in the measurements. And so there's been a variety of different studies looking at preparing for SWOT and characterizing the errors, and in particular, how to address correlated errors and things of that nature. So what I'll be talking about today is the use of some synthetic SWOT data in our REOPS system. So this is a system that we develop and operate at Environment Canada for a variety of applications, mostly internal to the Government of Canada, providing support for fisheries and oceans, national defense, Canadian Coast Guard for search and rescue, environmental emergency response, also the Canadian Ice Service in terms of their activities in the north, and various internal systems for Environment Canada and DFO for port modeling, electronic navigation, wave, storm surge, and coupling to the atmosphere. So you can see that a variety of these applications are very sensitive to surface drift, and thus having satellite altimetry and a capacity to constrain the mesoscale and even potentially the sub-mesoscale will be quite important to improve our capacity for these sort of surface drift applications. So a few words about the data assimilation approach we use. So this is a system that we ported from Mercator Ocean International in France. It's called the SAM2 Ocean Code. So it's essentially a reduced order extended Kalman filter that uses a set of multivariate background errors. So we currently assimilate 6 satellite altimeters. These are these nadir altimeters I was mentioning. We use this together with sea surface temperature observations from a variety of different satellite sources, as well as in situ sources. And then we combine this with temperature and salinity profiles from some of the sources highlighted on the right, so including floats, ships, moorings, marine mammals. And then you can see plots on the bottom there highlighting the kind of coverage we see for a typical nadir altimeter here for Sentinel-3A, and then on the bottom left, what we can get from a particular SWOT swath. So here, you can see how this 2D image allows you to get a better representation of the kind of eddies in mesoscale in the system. All right, so the way our experiments were set up, following previous efforts on doing some OSSCs and in other systems, is we take a particular model simulation that we use as our truth, our nature run. So here we use the well-known NATL 60 model simulation of the North Atlantic produced in France by Julien Le Sommet. This group is roughly a 1 kilometer resolution model of the North Atlantic. It's the same ocean model that we use in our system. So there's a certain similarity there, but at higher resolution, slightly different physics, different atmospheric forcing. So it provides enough differences that, it'll make it a little bit difficult for our model to achieve this kind of truth simulation. And then we do a series of experiments where we sample this truth the same way the real observations are sampled. So vertical profile, sea surface temperature, the nadir altimeters along their tracks. And then we add in synthetic SWOT observations using the SWOT tracks. Then we have 4 experiments. The first is just a free run to characterize the impact of assimilation. The first simulates conventional observations, so nadir altimetry, and then temperature, salinity profiles, sea surface temperature, and the sea ice. The second is where we simulate SWOT in place of the nadir, so to see if we get the same sort of behavior with nadir. And then the third is essentially adding SWOT into the current operational system. And so then the real question is, how close can we get to this truth? First results here are showing the impact on sea level anomaly. So standard approach, I'm showing on the right the root mean squared difference of the differences with the sea level anomaly observations here using Cryosat-2. So we can see in the OSSC 0 run, the free runs, we have somewhat larger errors in the Gulf Stream because it's free. The eddies are moving in their own way and showed sort of chaotic, uncorrelated variability with the NATL 60 run. In this OSSC 1 run, which is essentially our operational system, we can see we reduce these errors considerably. So the cooler colors then show smaller RMS. So we move then to assimilating SWOT in OSSC 2 and 3. We can see that these get reduced further. This is also highlighted by the panels on the right, where we can see differences in RMS. So red here showing a lower RMS. We can see when we simulate SWOT in place of nadir in OSSE2, you see a lot of red throughout the domain, so that's very good. And then in the bottom panel, even further improvements when we add SWOT to the nadir. So this is great, but these are the kinds of measurements that we can do in our operational system comparing to real observations. But the benefit of the OSSE approach is really that we can compare to unobserved variables and full fields by comparing directly to the NATL 60 solution, since we know essentially what our truth is here. So here is an example showing a comparison of 15-meter velocity errors. We chose 15 meters because it's close to the surface, but less strongly influenced by the surface forcing. And then also, it is semi-observed in the sense that we do have 15-meter drogue drifters, at least provide Lagrangian estimates in the real world. So at first glance, it's a little bit difficult perhaps to discern the differences between the runs in these plots because there's sort of a lot going on. But if we look at the time series of the velocity error variance averaged over the whole domain in this panel on the right, we can see then going from the free run in black to our assimilative run in red that there's already a significant improvement. But this improvement continues for the blue when we add in SWOT, and when we have SWOT and the nadir in the green curve, then we get the best solution. Providing overall something about 14% improvement compared to the operational run. So certainly not insignificant. So as I mentioned, SWOT not only adds sort of this two-dimensional element, but it also adds finer resolution. So we wanted to look at the wave number spectra of the errors as well. So we can see on the left the power spectral density of the wave number spectra over a box centered on the Gulf Stream. And then on the right, we can see in the upper panel the spectrum of the SSH errors. And we can see that right where the largest errors are at about 200 kilometers, that this is where we're having the maximum impact in decreasing the errors as we add in SWOT and SWOT and the nadir combined, giving the best solutions. We can see that we are able to use the observations adequately within the system, which was one of the questions a priori in terms of the potential benefits. And moreover, it does seem to lead to a net benefit in terms of the limit of constrained scales. So this is often estimated in terms of the spectral coherence line crossing the 50% threshold. And we can see here going from OSSE1, which is equivalent to our operational system, at somewhere around 300 kilometers. As we add SWOT and then SWOT and nadir, then we push this down to somewhere around 200 kilometers. So quite a significant gain in the scales constrained within the system. So quick snapshot here of some preliminary results with real observations. So these are observations that were released last December. So they're the release version 0.3. So they're basically 2 months of data covering September and October, or November last fall. And so our experiments are slightly different here. So now we're doing observing system experiments, so data withholding experiments, so OSEs. And the current operational configuration now has 6 satellite altimeters as compared to the 2 altimeters we had in our OSSE time period. So it's kind of the golden age of altimetry, really. So we had to do a further experiment, OSCE2, where we only have 2 altimeters. We could really repeat the same situation we had with the OSSE. So we look at that compared to OSCE3, where we have SWOT plus the 2 nadirs, and then 4, where we have kind of our standard operational setup with SWOT in there as well. And the panel on the right shows basically the impact, the RMS difference between the system with SWOT and the 2 nadirs compared to just the 2 nadirs. So the equivalent to what we did in the OSSE, and we see quite a similar response with quite a lot of red throughout the domain. Here too, we also have the Pacific, which we didn't have during our OSSEs, which is also showing a benefit, and even some benefit in the Beaufort Sea, which is quite encouraging. So since we see a similar impact in terms of the SLA innovations, then we could hope that we would also have a similar impact in our unobserved 15-meter velocities. So that's really quite encouraging. So we're very much looking forward to getting real-time feed and putting this in operations. And I just found out last week that the version 1 has been released, and so we'll be able to do a full year simulation now with this data. That's very exciting. So just a few final words. So this was really kind of a first step for us, foray into the OSSE world. So there's a bit of work to get set up in a framework where we could do this kind of synthetic observation test. But now that we have it, it opens the door to investigating other questions about, how we could optimize the marine observing program in Canada. So that's something we're thinking about. Also, as I mentioned, very much looking forward to assimilating real SWOT data in the coming months, and some extensions we're looking at are applying an eddy tracking approach, something we've done in the past to help look at what these RMS error differences really mean in terms of so with that I'll end there, and thanks for your attention.
Great presentation. Thanks, Greg. And it's nice to see SWOT coming online and see some real results, simulated and real results. And looking forward to hearing more as the data set starts to build up. Let me just check in the chat and the Q&A. Got a bit of a quiet audience so far today. So again, encourage everyone in the audience, please feel free to put your questions in the Q&A box and or in the chat. And remember, we'll have some time at the end of all the presentations if there are any questions that come in late. So please don't hesitate to share. Maybe more of a comment than a question for you, Greg, but it was interesting to see in a number of the plots you showed, it looked like going from just in the Aussies, going from just the nadir to nadir, or from just nadir altimeters to SWOT was an improvement. But when you had the altimeters and the nadir altimeters and SWOT combined, there seemed to be quite a big jump for at least some of the elements you showed. So any comments, thoughts on that kind of complementarity of them and how they seem to, I think it was for the velocity maybe, where there was a really dramatic jump when you had both combined, that they seem to maximize the value of these data.
Yeah, I know it's a bit of a contentious issue in some ways, because there's some proposals on the table about the future of the Sentinel next-gen satellite missions and whether or not they should go with 2 wide swath SWOT type altimeters versus 12 nadir altimeters. And I know there are 2 sort of published studies on this, and one showed that the SWOTs were 2 SWOTs would be better, and the other showed that the 12 nadirs would be better. And so so coming in as the third player in this debate, we haven't quite gone to the full 12 versus SWOT, but here the SWOT plus 6 is already kind of coming in the middle. So it is interesting to see that, our system is able to use that data adequately, because one of the hypotheses for why the 12 would be better is that you get, less wide of that width, but so you have less detail, but you have a more complete coverage and more frequently, whereas the SWOT overpass frequency is only 21 days. So you have lots of fine in detail, but then that will decorrelate in time between your 21-day overpasses. So that's a trick. And I think one of the reasons why it works here and we're able to manage both is that we have a 7-day assimilation window in what I was showing. So because of that, we catch more of these 21-day overpasses within the window and within the assimilation bubble, and thus we're able to make use of both sets of information a little bit better.
Great, thanks, Greg. And looks like we do have one question, so we'll hold off for a minute before we go to Richard. One question from the chat: the high coherence does not go to sub-mesoscales even with SWOT assimilation. Is it because the SWOT passes are too infrequent?
So, I mean, part of it has to do with how we assimilate it. I mean, this isn't a 1/12 degree system. So, we've essentially set it up more or less the way we run the operational system. We haven't done a lot of extra tuning for SWOT in this A. So I think there's a lot more to gain from SWOT. I think part of it is, I think as is suggested there, that it's the 21-day frequency that's having an impact. So I think that's part of it. But I think it's the filtering we apply to our error modes, and then also some of the errors we apply to, for example, the mean dynamic topography and in coastal regions. So that was one of the areas that we were interested in seeing benefits, was being able to constrain features closer along the coastlines. And it's something we haven't yet really looked into that much. That was one of our next steps. So we might be able to do a little bit better than was shown here in the spectral coherence plots.
Great. Thanks, Greg. So we'll move on to our last speaker for this session. We're just a couple minutes behind, but Richard, I'll make sure I give you your full 12 minutes, and we've got lots of time for discussion for you and all the other presenters after. So our last talk today is by Richard Lawford, Earth Observations and Water Food Connections in the Red River Basin. So go ahead, Richard.
Okay. Sorry, I don't know what happened to my presentation.
Yeah, we're seeing
I'm seeing a Zoom screen.
yeah. Maybe try unsharing
You see
it.
that? Do you see it now?
Not yet. Yeah, maybe try unsharing and resharing.
Okay.
There we go.
Okay, good. Sorry about that. My name's Richard Lawford, or Rick Lawford. I have current affiliations with the Group on Earth Observations and the Water Research Center at the University of North Dakota, although I don't get salary from anyone. This talk basically summarizes a workshop held last fall at the University of North Dakota, where we explored the role of Earth observations in developing water, energy, and food resources in the basin of the Red River of the North. The water, energy, food nexus involves looking at food security, water security, and energy security. And sometimes we can get better insights about food and water interactions by looking at this nexus concept. But clearly, while water and energy and food are important, when it comes to energy in the Red River Basin, it's a mix of fossil fuels, renewables, and etc. And the communities don't necessarily come with a unified voice to have the discussion as the food community and the water community do. So recognizing that water and food are priorities, we had a workshop that focused mainly on water and food, recognizing that energy security, land security, climate technology, and investments are also other important factors. We know that there's a lot of observations now being made of the Earth, and we've heard of some very sophisticated approaches in the previous talks to how that data can be used. But in the case of NASA, for example, this is their Earth fleet. And the question arises, how can we best exploit this large investment in Earth satellite information to improve water and food security, and in specifics, in a particular geographical area? So that was the purpose of this effort. And within the geo activity, we have a pilot initiative related to Earth observations for the water, energy, food nexus. We have three themes. One is technology, where we're looking at agrivoltaics and other renewable energy technologies. We also have some modeling activities where macro-scale modeling of the agricultural impacts on water quality in the Mississippi River Basin is being undertaken. And then we're looking at information systems. And in particular, we want to develop an information system for the WEF Nexus resources in the Red River Basin. Red River Basin, as those of you who live in the Winnipeg area will know, takes the drainage that comes from the basin into a river, the Red River, and that river goes from basically South Dakota up to Lake Winnipeg. Mainly in this basin, there are a lot of agricultural activities, corn, wheat, soybeans, sugar beets, potatoes are growing. 1.8 million people live in the basin. 1.2 of them are in cities, the rest are in farms. And it is an interesting case where transboundary issues are important because it shares two countries. It also has two states involved, particularly North Dakota and Minnesota, which are quite different in their approach to policies related to the environment. In terms of the geomorphology of the basin and the hydrology, it has a flat topography. Very extensive shallow flooding occurs during the spring, during the breakup. The clay soils along the channel of the Red don't readily absorb water. There's also the difficulty of Devil's Lake, which has a intermittent flooding of lands around the lake as levels rise. And the reasons for that relate to precipitation, but maybe also land drainage, because it's used extensively by farmers in the U.S. portion of the basin. They want to get the water off their land and into the river channel as quickly as possible. And so they drain the land. So we looked at how Earth observations could be used in different ways within this need that's formed by the Red River Basin, and tried to identify where there were gaps in what we could do and what we needed to learn from the data that was available to us. So one area that people want data for is to improve flood management. So disaster risk management is an important issue, particularly when large spring snowpacks melt and there's high spring moisture and rain on snow events. It causes a lot of flooding, and as a result, there's several ways that people address this. One is by thinking about water diversions. Another is by thinking of retention ponds. And then the farmers themselves, as mentioned, they worry about draining the water off their lands as quickly as possible. There's also issues of water quality, because the water that comes up from the U.S. often is enriched in nitrates and phosphates from farm fertilizer, and these are transported to Lake Winnipeg, where phytoplankton blooms occur. So the question arises is, how can we use Earth observations to monitor the process? Can we get some insights into when those phytoplankton blooms are about to emerge? We also looked at the farm production activities and how that is managed. Soil moisture is very important for plant growth. The data that can be used to determine when to plant, when to cultivate, when to irrigate, and irrigation is not used very much, I should note, in the basin, but still important. Soil moisture products are available, particularly SMOS products, which seems to be pretty reliable, but it is very coarse resolution and not sufficient to resolve the information needed by the individual farmer. Winter snowpacks influence spring soil moisture availability, and so we need to think about strategies to retain snow on the land a little bit longer, and also to be able to measure the snowpack and identify how much water is going to be coming from that snowpack. Other things that affect the operations of a farm include the precipitation, the timing of snowmelt, for example, as we noted, affects when to plant crops. But precipitation events occur throughout the year, and so they're important during the harvest because it delays the harvest. It can affect field operations as well. So we need to make better use of available data, and the GPM constellation provides data. We heard a good sales pitch on the iMerge precipitation product during the workshop, and it perhaps has potential for snow measurements as well. We intend to explore that. We also learned about the benefits of the Landsat data, which has been around for a long time, and it can be useful for drought monitoring. This is kind of moving ahead on me. I need to go backwards here. So I'll just go to the slide now. The Red River Basin has some interjurisdictional challenges we found, in that the data is not used in the same way in the different authorities or jurisdictions, and these in situ data services are not uniform, with a lot denser in situ networks due to a mesonet in North Dakota than in the rest of the basin. So in the decision-making process, a lot of communication is needed between the different jurisdictions, and it's not clear that that always happens. So as we looked at the needs within the basin, we need information to support decision-making at the farm scale. And the data sources themselves, like soil moisture and a lot of the sensing that's being done, does not give us that resolution. So we need to supplement that with models. Measurements and data products for snowfall and snow on the ground across the basin are very uneven and need improvement. People were most concerned about snow and the fact that in some jurisdictions, the snowfall measurements are going away. And in other jurisdictions, a lot of reliance is being placed on automatic snow gauges, which aren't providing very good information, and that there's no record on what type of gauge is being kept. So the curation of the data is not good. NASA is expanding its data services, but that isn't being communicated to indigenous communities or farm communities. Many of the people who were representative of the indigenous community were indicating that they were unaware that these data sets existed. They didn't know how to get them, who could provide them with advice. They didn't know. Some of the other needs included the fact that we have a lot of process models for things like erosion, but there's not in situ data that's sufficient to calibrate these models to the level in which they need to be calibrated. And finally, we heard about opportunities with living laboratories and AI for monitoring and improving the products that are available to people, but we don't fully understand them and we need to develop them. So in summary, the water security issues were well covered in the discussions. Food security, not so much, and we didn't really touch on energy security very much at all, except for the new power data sets that are being produced by NASA. The workshop identified some data gaps and differences in services in the three responsible jurisdictions. The soil and snow processes were basically areas where more in situ data were flagged as being needed for calibration and validation. And that was particularly true north of the 49th parallel. Examples of new approaches such as information systems, living labs, human-centric climate services, and AI were introduced. And this would enable the audience to learn about new approaches that could be applied in the basin. So I think it's very important for people who are working on new sophisticated products to find good case studies that will allow people who are generalists like myself to sort of carry those ideas through to the communities where they could be used effectively and meet some pretty important social needs. So thank you for your attention. And if anybody's interested in following up, you have something that you think you could contribute, I'd certainly like to have a discussion with you at some point in time. So thank you.
Great. Thanks very much, Richard. Really interesting talk and great to hear a little bit of a different perspective and really that focus on the end user client end, which is something that as scientists we're often far enough removed from, that we need to keep that top of mind of how is this data, how are these products we're developing really going to get used by real people to help issues in the real world. So really appreciate that perspective on how that can be applied in terms of water and food in the Red River Basin. Just let me check the Q&A quickly. Don't see any new questions yet, but I had a couple for you. First, you were talking about the discussion on the needs for products and information at the farm scale. I'm wondering, within the Red River Basin, if we think about it from an EO perspective, we define our products and the data in terms of spatial resolution, our products typically in terms of a grid spacing. What kind of scale, what kind of resolution are they looking for? I'm curious what type of size of farms is typical in that area.
Yeah, it's fairly large farms in some cases. If there were products at 2 kilometers by 2 kilometers, that would be useful, or even a larger scale, but 25 by 25 kilometers is really too big, particularly in the summertime when you get convective storms coming through and they want to know, did the storm affect us or did it affect the farm next to us? And there's also the insurance requirements that are needed to be met with data. And satellite data could provide a major input there, but people tend to rely on the nearest rain gauge, which may be 10 miles away because they don't have the confidence in the satellite data.
Well, I do have one good thing to share is that Canada's looking at a terrestrial snow mass mission, a concept satellite mission that we're looking at. That would be a KU band synthetic aperture radar system, building on the heritage we have from the RADARSAT program. It's not funded yet, but there's colleagues at Environment and Climate Change Canada's Climate Research Division working on the terrestrial snow mass mission, or TSMM, which we're hoping will help address this gap in understanding the snow water equivalent stored in the snowpack on a weekly basis for all of snow-covered areas in the Northern Hemisphere. So hopefully we can fill one of those gaps, although satellite missions take a long time to develop and launch. So that's probably closer to 10 years away than it is to today. But hopefully we can secure funding for that mission and start to address that gap.
Who's the lead on that, by the way?
Chris Dirksen, who's a scientist
Chris, okay.
at the Climate Research Division here at Environment and Climate Change Canada, Chris Dirksen. In terms of data access, you noted the workshops talked a lot about the challenges. Do you have any comments on, being someone interacting directly with the public, comments on thoughts on how we can start to make our products more accessible, more and increase awareness? Are there any best practices or tips or lessons learned from the comments you received from the workshop participants that you could share with the audience here today?
I guess what is clear is that there are services that are provided by individual agencies, products that come from individual agencies or individual sources, maybe even a research product that comes, but they're not integrated into a single package. And if the user could go to a single place where he could get access to NASA data, access to NOAA forecasts, access to Environment Canada products, access to other types of information, that information platform could be as one go-to place. And that integration is something that we're trying to explore with our project, is to see if we can use the paradigm of the water, energy, food nexus to bring at least 3 sectors together of information that a person needs for a complete package of their functions and their operations.
And I can see how in a transboundary and multi-state on the US side that adds a lot of extra complicating factors in trying to achieve that. So yeah, really interesting talk and great thoughts, and thanks for those insights. I'm just going to check the chat and the Q&A again to see if there's anything more for any of our speakers. And I don't see any more questions, but there is a bit of... Go ahead, Richard.
Sorry, I did have a question for the first speaker in the session on the RADARSAT. I wondered if they were able to measure the depth of the snowpack, like he was talking about melting of ice, ice versus no ice, snow versus no snow. I wondered if he could measure the snow depth over the land surface or the thickness of the ice with the RADARSAT backscatter, or maybe that's too far down the line. Don't know.
Hi, thank you for the question. Yes, so currently we are not able to measure snow depth, unfortunately. We may be able to potentially discern a signal of snow-covered ice versus ice that does not have snow cover, because we do see a difference in backscatter. I didn't talk about this much, but when there's a snowfall event, we do see that the backscatter following that is impacted. But snow depth estimation, I'm aware that there are some retrievals based on passive microwave that they're able to obtain snow depth. So that could potentially be possible in a distant future, but that would be highly uncertain and it would be a rather complicated process. So in short, the answer is no, but that's a very interesting prospect.
Okay, thanks.
Yeah, maybe I'll add a little there from my past life as a radar scientist, that at C-band, the wavelengths of the RADARSAT satellites is about 5 centimeters. So it penetrates through the snowpack relatively easily with little interaction with the snow grains. The terrestrial snow mass mission is going to a much higher frequency in KU band and actually using 2 different frequencies within KU band. So a much smaller wavelength that has more interactions with the snowpack. So leave it to Chris Dirksen and others to explain that in more detail, but that's part of the driver to move to a different frequency band for snow observations. I see one more question. This would be for you, Alec Sabai. For RCM lake ice monitoring, what's the reason for the backscatter increase after melt onset?
That's a very good question. We are not currently sure for that, because you would expect that it would potentially decrease given that, there's more surface roughness happening and so on. Could potentially be some contribution from the formation of melt ponds, which have a highly reflective surface, more comparable to, but it is quite hard to tell. It may be, sorry, so there are many different possible factors. Could be potentially contribution of melt ponds, potentially just there being less surface roughness, given that the snow surface is being replaced by smoother ice. But that is something that we are looking into, so I cannot provide a certain answer there. Thank you for the question.
Thanks, Alex. All right, and I'll give a few more seconds and we'll see if we get any more questions come in. In the meantime, I'd like to thank all of our presenters today for a wonderful session. Thank all of our presenters over all 4 parts of the Satellite Earth Observation sessions. And thank my co-chair, Kaley, for her help through the sessions yesterday, and wish her the best in her meetings today. And I don't see any more questions, so I believe with that, we can close it out. Encourage everyone to keep attending sessions through the week. Enjoy the remaining presentations and plenaries. I'm just going to check the schedule quickly, see if there's anything to note through the rest of the day today. So we have two more presentation sessions in sessions 3 and 4 today. And yeah, please make sure to attend the plenaries Wednesday and Thursday. Some great talks, it looks like, lined up there. And wish everyone an excellent remainder of CMOS. Thanks for tuning in, and hope to see all of you soon.
Thank you for organizing the session.
Thanks, everyone.
Thanks, Alec.
Thanks, Alec.